The issue I want to take up today is the first issue in the domain of inferential statistics, and that's the issue of estimation. Let me just overview this for you, and there's no need to write this down because we will be going over it in much greater detail. Estimation is, I think, a process that's at least the end result of which is very familiar to you. I'm sure that you've heard reports of the sort. 62% of Americans polled gave the president an A or a B for his performance in office. And the margin of error, you're told, is plus or minus 3 points. Or you're told that in the run-up to an election, that a certain percentage of people have indicated they will vote for a particular candidate. 52% have said they will vote for Bush, 48% for the Democratic candidate. And then you're told as well that the margin of error is plus or minus so many points. That's nothing more than rudimentary estimation. It's an example of interval estimation. We're going to start our discussion by examining something even more rudimentary than interval estimation, and that is point estimation. So let's take a look at the issue of point estimation. And I think it worth your while during this discussion to think in terms of central limit theorem. I try to impress upon you the significance of central limit theorem, and central limit theorem underwrites all inferential statistical procedures, including estimation procedures, as we shall see. If I had at the beginning of the semester set you the task of estimating the average IQ of all adults living in Katy, it may have occurred to you that, I presume it would have occurred to you at some point, that you couldn't administer a test of intelligence to all adult residents in Katy, certainly before the end of the semester. I presume then you would have selected a sample somehow, and I will assume that you did that randomly. You may have even thought to select what might be considered a large sample, and let's assume that is so. Let's assume that you selected a sample of 200 persons, 200 adults living in Katy, and you administered a test, a standardized test of intelligence to those 200 people. Let's assume further that the average score on the standardized test of intelligence by those 200 persons was 105. Let me ask you, what would be your best guess of the average IQ of all adult residents of Katy? That is, if you knew the sample mean, X bar, or we've sometimes called it M, was 105.0, what would be your best estimate of mu, the population mean? It's not a rhetorical question. We're going to sit here until you get this one right. This is like Brussels sprouts. You're going to eat them. I don't care whether you eat them hot, warm, or stone cold, but you're going to eat them, sort of. No, I wouldn't make anybody do that, but I would make you answer this question because it's pretty straightforward. Could you? 105. One meek voice says 105. Since that's, if we remind ourselves, that was the sample mean. Your best guess of the population mean, if the sample is large and has been selected randomly is the sample mean. Because under those circumstances, that is when sample size is large and when the sample has been selected randomly, the sample mean is an unbiased estimate of the population mean. Would you agree? Would you not agree? Would you violently disagree? Would you accept it because I said so and I'm sort of an authority figure in the class? Okay. If that's why you'll accept it, that's fine. I prefer that you accept it because we talked about the issue in the first part of the semester. I think we said 3 or 4 times, I know we said at least 3 or 4 times, that sample estimates are unbiased estimates of the population parameters when sample size is large and when the sample is selected randomly. At least when we're talking about sample means and sample proportions. That's not the case, if you recall, when we talk about sample standard deviations or variance, because when we were discussing computation of variance and standard deviation, it was you needed to know whether you were dealing with a population or a sample because it altered the denominator. When you were computing sample variance and standard deviation, you used n-1 rather than n, and you did so in order to correct for bias. But in the case of sample means and sample proportions, if sample size is large and if the sample has been selected randomly, your best guess of the population parameter is on the one hand x bar or m, the sample mean, and on the other p subscript s, which is simply notation for the sample proportion. So you've conducted this study in Katie. You've selected 200 adult residents of Katie. You've administered the standardized test of IQ. You've discovered that the average test score is 105, and you reported to me at the end of the semester that your best guess of the average IQ of all Katie residents is, or adult residents, is 105. How likely is it that that's really the case? How likely is it that the average IQ of all adult residents of Katy is in fact 105? Would you invite
No, it's not very likely.
I would say it's extraordinarily unlikely. I'd bet the farm, if I had a farm. I'd bet the house. I'd also bet my dog, but I'm not very keen on my dog right now, so I don't make a lot of that. But I'd bet the house and the car, and I like my car. I'd bet the house, the car, and the washing machine that the average score of all Katy residents was something other than 105. The issue is this: if we think in terms of central limit theorem, we have a sampling distribution of sample means. That sampling distribution of sample means has a mean of mu, and it has a standard deviation of sigma over the square root of n. Would you agree? I hope so. Because if you don't agree to this, if you don't recall this, it's time to check out. The question I'm asking is, how likely is it? This is an infinite number of sample means plotted here. This is a distribution, a sampling distribution, so it's a distribution of an infinite number of sample means. How likely is it that your single sample mean lies right at the center of this distribution. How likely is it that this sample mean of 105 is right at the center of the distribution? It's extraordinarily unlikely. It's much more likely that your mean of 105 is somewhat below the center of this distribution or somewhat above the center of this distribution. So you have this paradox. On the one hand, because of the way you sampled randomly and you sampled a large number of people, your best single guess of the population mean is the sample mean. But at the same time, you recognize that it's extraordinarily unlikely that in fact the sample mean x bar equals mu. And that is why point estimation is essentially useless. Because while point estimation generates a best guess, it generates a best guess that is unlikely to be right. What is much more useful is interval estimation. Interval estimation. That is, let's try and estimate mu. An unbiased estimate of mu is x bar. That was the point estimate. Would you agree? That mu equaled x bar. That is, an unbiased estimate of this score, mu, is in fact x bar. Anybody disagree with this? Anybody lost by this? Anybody saying, I'm not sure how you got there? Speak now, forever hold your peace. What we're now going to do, however, is create some interval, some range of scores around the mean. That is, we're going to add some score. We're going to subtract and add some score to x. Some score that represents the same distance above the mean as it does below the mean. That is plus or minus 3 points or plus or minus 6 points. That's when you watch TV or listen to the news, read a magazine, whatever, and you're told that that 48% of persons support a referendum, the margin of error is plus and minus 3 points. X bar here, and we could be talking about a sample proportion, but we happen to be talking about a sample mean. That's the 48%. In fact, that would be a proportion, obviously, but that is the analog to the 48%. The plus and minus x, the plus and minus 3 points, is the margin of error. So you have, this equals x bar plus and minus, would you agree, some number of standard deviations. Because the distance along this x-axis can be measured in units called standard deviation. So that if we're now moving from point estimation to interval estimation, we're simply supplementing the point estimate with some range of scores, a range of scores that can be measured in units called standard deviation. Let me go back here. Otherwise, I think I'm going to get to the end of this story, and it's going to be like some of your drives home, some of my drives home. You'd pull up in your driveway and you go, how on earth did I get here? Yeah. We're going to get to the end of this story and we're going to say, how on earth did we get here? First of all, we keep in mind the sampling distribution of sample means. And central limit theorem says that that sampling distribution of sample means has a mean equal to the population mean mu, and it has a standard deviation equal to sigma over the square root of n. That's I think, one statement. A second statement is that if we're estimating mu, we started with the point estimate, x bar. X bar, because that is the sample mean, because the sample was large and it was selected randomly, provides an unbiased estimate of mu. We recognized, however, that this point estimate was unlikely to be accurate, but it nonetheless provides an unbiased estimate of mu, the score at the center of this distribution. We then made this transition to interval estimation, which is a much more useful and a much more powerful statistical procedure. All the interval estimation involves is establishing some range of scores around that unbiased estimate, in this case x bar. And if we think in terms of a sampling distribution of sample means, we can talk about then a range of scores, either plus or both plus and minus, some range of scores that can be measured in units called standard deviation, because the distance along this x-axis can be measured in units called standard deviation. We did that when we talked about z-scores. Z-scores were standardized scores. They were measured in units called units of standard deviation. So we can talk about some number z of standard deviations, and the standard deviation of this distribution is sigma over the square root of n. And lo and behold, I'll bet you a horrible thing happens. That if you look on page 163 of the text, formula 7.1 says CI, that is confidence interval, that is nothing more than an estimate of mu, equals x bar plus or minus z multiplied by sigma over the square root of n. That is, in order to estimate mu, all you need is information about x bar, information about sigma, information about n, and some z-score. That z-score represents the distance you have to travel along the x-axis. Z is a function of the confidence level of the estimate. It's a function of the confidence level of the estimate. Now, while we could adopt any level of confidence, by convention there are two. 95% and 99%. If you adopt a 95% level of confidence, you need a z-score, you need an area, you need to identify an area that includes 95% of all of the area under this curve. That is, it includes 95% of all possible sample means based upon a sample, in this case based upon a sample size of 200 drawn randomly from our population. If you adopt a confidence level of 99%, you need to identify boundary markers, and that is, you need to define an area that incorporates 99% of all of the area under this curve. That is, incorporates 99% of all possible means drawn randomly, or all possible means based upon samples of 200 drawn randomly from our population. If you were to go to Appendix A, looking for a z-score that had associated with it an area beyond z of 2.5%, that is 2.5% up here, 2.5% down here, a total of 5%, that is if you adopted a 95% confidence level, you would discover that you have to go plus and minus 1.96 standard deviations in each direction. If you go 1.96 standard deviations below the mean and 1.96 standard deviations above the mean, you define an area that includes 95% of all scores in the distribution. If you were interested, if you adopted a 99% confidence level, that is, if you went to Appendix A looking for a z-score that had associated with it an area beyond z of 0.5% up here, 0.5% down here, you would discover that you have to go 2.58 standard deviations in both directions. That is, if you go 2.58 standard deviations below the mean and 2.58 standard deviations above the mean, you isolate an area that includes 99% of all scores in the distribution. You don't need to do that. You can do that, but since we will always be using either a 95% confidence level or a 99% confidence level, all you have to do is commit to memory 1.96 and 2.58. That is, if you're estimating mu, and you adopt a 95% confidence level, that estimate of mu will be x bar plus and minus 1.96 multiplied by sigma over the square root of n. If you adopt a 99% confidence level, that estimate will be x bar plus and minus 2.58 multiplied by sigma over the square root of n. This is a long way from, well, we took this sample of 200 people and it was random, and so our best guess of the average IQ of all adult residents of Katy is 105. You're now, as we will see, you are now in a position to say, I'm 95% confident, or I'm 99% confident, that the average IQ of all adult residents of Katy is between some score here and some score here. That's what researchers, or actually it's not what researchers are saying to you, it's what news readers are saying to you when they tell you that 38% of those polled supported a war with Iraq. The margin of error was plus and minus 3 points. They're telling you that 38% was the point estimate. That's the percentage of the sample that indicated they would support a war with Iraq. When they say the margin of error was plus and minus 3 points, they mean 3 percentage points. So what they're and because these surveys are typically conducted or calculated at a 95% confidence level, what that statement says is that the researchers are 95% confident that somewhere between 38% minus 3%, which is 35%, and 38% plus 3%, which is 41%, support war with Iraq. And that is a long, long way from slaughtering wild animals and looking at their entrails. And it's a long, long way from, I suspect, where you would have been at the end of the semester had I set you the problem at the beginning of the semester to estimate the average IQ of adult residents of Katy. This is absolute magic. It's absolute magic. You're now precisely confident. You can articulate your level of confidence. What being 95% confident means is that there is less than there's a 5% chance of your estimate being wrong. That in this instance there is a 5% likelihood that either fewer than 35% or greater than 41% of Americans would support war with Iraq. That's why in political polls, come election time, you and I are stunned if the pollsters are wrong. We're absolutely stunned, and they are stunned if they're wrong. Yes.
What did you say CI was again? Use something? The CI?
In the question is, what does the CI stand for in the formula in the text? It simply stands as it says here, where CI equals confidence interval.
You said it was like mu something?
Okay, yeah. It stands for confidence interval, but we could just as appropriately write mu estimate. This is an estimate of mu because it's based upon x bar. It's based upon a sample mean. You can only use a sample mean to estimate a population mean. So this could be just as validly read. Estimate of mu equals x bar plus and minus z, which would be either 1.96 or 2.58, multiplied by sigma over the square root of n. And sigma over the square root of n is the standard deviation of the sampling distribution of sample means, at least according to central limit theorem. And I say that to in fact encourage you, as you read through the material relevant to this, and there are three situations that we will look at here. And we will look at them in detail. Next time, we'll take up this situation. That is, where you're estimating mu and you know sigma. We will start with that situation. We will look at two others. One where you're estimating mu again, and one where you're estimating p subscript u, which is the population proportion. But that will, I think, only make conceptual sense to you, and it may only make computational sense to you if you look back to central limit theorem. Sampling distributions, particularly sampling distributions of sample means or of sample proportions, are fundamental to interval estimation. But even more fundamental is central limit theorem. Because central limit theorem tells you about the attributes of this curve. It tells you the attributes of this distribution and the circumstances under which this distribution and those attributes obtained. N must be large and the sample must be selected randomly. And if those two conditions are not fulfilled, then all of the logic of central limit theorem helps you not at all. I would also point out that if you reflect on when we were talking about measurement reliability and measurement validity, if you have unreliable measures or if you have invalid measures, all this trickery is of no help. If you have unreliable measures, those measures will generate unreliable data. So the information, the data that you're working with is unreliable to start with. That is, the data themselves, the observed scores, are poor estimates of true scores. So that if you start with unreliable data, it's really a matter of garbage in and garbage out, and the rest of the stuff in between doesn't change that. So for all of this logic to be useful, all of those other issues that we've discussed, dealing with reliability and validity and so forth, have to be met. Are there any questions about this preliminary discussion of point estimation and interval estimation? Hearing none, we will next time move through an example of this circumstance, and though that is, there are examples presented to you in the text, and we will look at, as I indicated, two other situations: another situation in which we're estimating mu, and one where we're estimating the population proportion p subscript u. But that discussion is contained in the text with the relevant formulae, and while those formulae change, they change in a systematic way so that you find that the general form of the formula remains stable. And we will start that next time.